so just going over some terminology that we looked at yesterday. Here's some function below k of x, and we want to know a critical number of k of x. So just to remind, critical number does not mean where f of x has a min or a max. So oftentimes where there is a critical number, there is a min or a max. It doesn't mean where the function has a min or max. The critical number defined is where the first derivative is 0 or undefined. So in this case, where is the derivative 0 or undefined? Here, here, here. In all of those cases, the tangent line, k prime of x, equals 0 when x equals -2, 0, or 2. And in each of these cases, this is a min, and max. So in this case, each of these three critical points are local min or max, but let me just, for demonstration purposes, draw another graph that looks like this. And let me make that even more clear because it looks like there's a min there. As we come down, we're going to have a slope of 0, but then go right back down. So at this point right here, if we call this function h of x, if that function is h of x, and this is the point a, h prime of a equals 0, because it's having a slope of 0 there. There's no max or min. A is still a critical number, even though it doesn't correspond to a local max or min. All right, so yesterday, or in the last video, we were talking about concavity, and you've already seen this, but the idea, concavity, for something to be concave up, our function is going to look like this, and for it to be concave down, our function is going to look like that. And so let's get this better color coded. So here's concave down. And where's it concave? So looking at my function, where's it concave down? It's concave down from here to here. And where is it concave up? From there to there. And where we switch concavity, is called the point of inflection. That's where we switch concavity. And wherever you switch concavity, if you think about the derivatives or the slopes, right at A, we've got a slope of 0. It's getting more and more negative until C. So the slope is getting more and more negative until C. But afterwards C, our slope is getting more and more positive until here it's 0, and then it's positive thereafter. So at the point of inflection, our derivative function always is going to have a local max or min at the point of inflection. Now let's just kind of look at just a random graph here of some function. So you can start seeing points of inflection in concavity. To be consistent with what we were doing before, we were saying blue is concave up, red is concave down. So blue is concave up, red is concave down. So we're concave down to here. And that's where my graph is the steepest. And then we're going to be concave up. And here my graph is the steepest. Now I'm going to be concave down until I'm the steepest, and then once again concave up. Okay, so if we call this, point A, and point B, and point C, then x equals A, B, or C, we have a point of inflection. And at A, so f prime of A, our derivative at A is going to be the most negative. We're going to have a local minimum value. And then our derivative at B, that's where we're the steepest. So FB is the most positive. So we're going to have a local max. And at C, our derivative at C, we're going to be the most negative there, the steepest going down. So it's going to be the most negative. So we're going to have a local min. Now, trying to tie this all together, when f prime of x has a local min, which it does at A and C, when my derivative function has a local min, well, what's going on? In both of those cases, we're going from concave down to concave up, and this will always be the case. Similarly, when f prime of x has a local max, like it does here, we're going from concave up to concave down, and this will always be the case. So now we can start recognizing a relationship between the concavity and the derivative function. So when the derivative function has a local min, it goes from concave down to concave up. When the derivative function has a local max, it goes from concave up to concave down. All right, more on concavity. If the slopes of a function are positive, but decreasing, so think about it. Slope being positive, but it's decreasing. So there's one slope, there's another slope, there's another slope. All those slopes are positive, but decreasing. What is the concavity here? Well, if we were to connect those lines, what does it look like? Concave down. What about if the slopes of a function are negative but increasing? So here's a negative slope. Increasing means becoming more positive or less negative. So increasing, increasing. All of those are negative slopes, but they're becoming less negative. What's the concavity there? Well, connecting the lines. Clearly that's concave up. So what conclusion can we draw from this? The conclusion that we can draw from this is if the slope f prime of x, so if the slopes or f prime of x, if the slopes are decreasing, so if the slopes are getting less and less and less, if the slopes are decreasing, then our function is concave down. And if the slopes, f prime of x, are increasing, then we're concave up. And let's see that. So in red, doing this first one, if my slopes are getting less and less and less, so I've got steep slope, less slope, less slope, less slope, less, we get this concave down. And in the second case, my slopes are increasing. So steep. Now more positive, more positive, more positive, more positive, even more positive, we get concave up. So now, tying this together with a challenging problem, let's think about this derivative function, and we want to be able to eventually sketch a possible graph for f of x. So starting up, what are the critical numbers of f of x? Well, the critical numbers are when f prime of x equals 0. And luckily, this is factored out nicely. So we know that f prime of x equals 0 when x equals 2, -5, or -1, using the zero product property for a function fully factored. Okay, so for what values of x is the original function increasing? So for f of x to be increasing, that means that f prime of x needs to be greater than 0. Well, here I'm going to implement a technique that we're going to be using a lot. So we're going to be looking at values of, we're going to create a chart looking at values of x and f prime of x. And we're going to look at the critical numbers and then to the left and right. So we're going to look at when x equals -5. We're going to look at when x equals -1. We're going to look at when x equals 2. And then we're going to choose values to the left and right of those. So let's just say like -6, -4. -4 is between -5 and -1. 0 and 3. And we're going to do this so that we can inspect what happens to our derivative function for values of x at the critical numbers and to the left and right. Well, okay, so starting up, we know that for these points, my derivative function is 0. So we know it's not increasing. Now let's look at when x equals -6. So f prime of -6 equals, and all we care about is whether our derivative function is greater than 0. So if I plug -6 in, we get -6 minus 2 squared, -6 plus 5, -6 plus 1, and that equals a negative number squared times a negative number times a negative number. So negative number squared is positive, negative times a negative results in a positive number. What about when we plug -4 in? So f of -4 is a negative number squared, because that would be negative. -4 plus 5 is a positive number, and -4 plus 1 is a negative number. So we get a negative number squared times a positive times a negative results in a negative number. What if we plug 0 in? So this is getting a little bit messy, but if we plug in f prime of 0, it's going to result in a negative number squared times a positive number times a positive number. So negative squared is positive times a positive results in positive. And if I plug in when x is 3, so f prime of 3, we get a positive number squared times a positive times a positive. And remember, we're not looking at numbers. We're just trying to decide whether or not our derivative is positive or negative so we can figure out when the function is increasing. Because when f of x is increasing, our derivative must be positive. We just showed that f prime of 3, just showed that f prime of 3 was a positive number. So where is the original function of f of x increasing? Well, it's increasing from x equals -infinity all the way up to -5. Because we know that it's positive from -6, and because the critical numbers occur only at -5, -1, and 2, it's never going to change sign in other places. I'm going to continue this video